Hello everyone, this is the second chapter of our electrical measurement and instrumentation book. In this chapter we will read about the analog instrumentation and the electromechanical instruments. So moving in, these are the contents of our today's lecture. We will first study about the electromagnetic and electrothermal type instrument, which are basically the analog instrument. After that we will study the principle of operation of some instruments, and then the operating torque, the damping, deflecting and controlling torque, and after that we will study the structural details such as the suspension, the Taut suspension and pivot and jewel bearings, and after that we will also have some discussion about this torque to weight ratio, which is a characteristic by which we can measure the effectiveness of an electromechanical instrument. And after that we will also study the controlling system. These controlling systems are used in electromechanical devices, the measurement devices, and these control system include spring and gravitational based control. So as the name suggests, we will be studying about the spring mechanism as well as the angle and gravity, etc. Also we will study about the damping systems as well, that what are the types of damping system, what material or the fluids, etc. that are used inside this damping systems. After that we will also study the PMMCs, permanent magnet moving coil instruments, and after that we will also solve some problem on these instruments. We will study topics related to swamping, resistors, etc. as well. After studying this PMMC, we will convert the same PMMC to an ammeter, a voltmeter and an ohmmeter, so that we can also know about the uses of these PMMCs. And in the end, as these instrument uses some direct current based mechanism, so we will also study instruments that are used for AC current measurement. So these instruments are termed as electrodynamometer type instruments. So this is the content summary of our today's lecture. So starting with the analog instrumentation, an analog device is the one in which we see its output a continuous function of time. So in these instruments we can graduate a scale. You can say this is, let's say, our scale, but we can then further add magnified point to it, and even after adding these points we can further see that there are many other points inside these graduated points. So such undefined points or the divisions refers to an analog output scale. So we can have infinite possibilities and a possibility inside possibilities as well. We will further see that these instruments are designed using some phenomena such as electromagnetic phenomena, electrostatic phenomena and electrothermal phenomena. So these phenomena are briefly discussed here. Electromagnetic phenomena is the one which utilizes magnetic effect for the magnetic effect of electric current. So these type of instruments are termed as electromagnetic instruments. Electrostatics use the charges and the forces that are appearing on the charge. So static forces are dealt in here. Here the dynamic forces are dealt. The rotation of an electron gives us magnetic field, so we deal magnetic in here, and here we deal the charge on the electron. So here the static charges are dealt. Electrothermal utilizes heat effect, such as thermocouple uses the effect for changing voltage over temperature change. So these type of instruments are generally analog instruments. Why these are analog? Because the effects, the forces are of continuous nature. these are not some forces in which we can say that there is one force plus second plus third. In electrons, on electron level we can say that, but on larger scale such as currents we cannot say that. So that's why these are instruments are termed as the analog instruments, because the B is in the form of, let's say, 0.9 into 10 power minus 3. So this type of instrument, this is Weber per meter square. So these type of instruments are continuous nature and are referred as analog instruments. These effects, the effect of heat produced by current in a conductor is used in thermocouple. Electrostatics is used in static voltmeter, so we find voltages using some capacitor, etc. The electromagnetic induction based instruments are wattmeter, induction meter, etc. So these meters uses these three phenomena. Principle of operation of many analog instruments has remained magnetic principle, or the heating effect principle, the electrostatic, electromagnetic, and Hall effect. You people are known with these effects. Magnetic effect is that in the vicinity of a magnet, let's say this is north, and we place another north, so this north will repel this north. So this is the magnetic effect. Heat effect is that the convention of heat, that if we heat up this side, this heat will transfer towards this colder side. So this is the heat effect. And if we combine this heat with some thermocouple type, so then we have two different materials, and its heat effect can tilt this thing on either side. Okay, the electrostatic effect is the effect in which we see the amount of charges stored. So this diagram basically tells us about the electrostatic, that if we have same charge on this bulb, it will neither move here or here, but if this bulb is a bit negative, then it will move towards positive. If this bulb is a bit positive, it will move towards negative. So this will tell us that what is the nature of the charge stored on this bulb. So this is the electrostatic effect. Electromagnetic effect is that when we place a current carrying wire inside a magnetic field, it will experience some force based on the Fleming left hand rule directions that are given. So this force is F is equal to BIL sine of theta. So this is the electromagnetic effect. In Hall effect, we see the movement of electron, the radial movement of electron, and this radial movement gives us a charge on a plate. So if we have, let's say, this plate, and we pass some current through it, and then we apply some magnetic field through it. So let's say this is an electron. This electron will start rotating around this field. So this says that the electron will go toward this side, or let's say a positive charge will be stored on this side. So we can measure this voltage using some external voltage measurement instrument. So this will gives us the mechanism of Hall effect. In Hall effect, we place a plate, we pass current through this plate, and in the 90 degree to that current plate, we get the output voltage and we measure it. So the amount of voltage developed on these two terminals depends upon either the current that is passing, more current, more voltage developed, or the magnetic force that is being applied to it. So more magnetism, more voltage. Normally this magnetism is kept constant, and only the conductivity of this material is checked by this current. Moving toward the next topic, we are having many types of mechanical instrument in which only the torque is responsible for its measurement. So if we check this instrument, let's say this type of instrument, so these instruments are having some springs and some, let's say, moving parts or some stopping part. So these instruments uses some torque mechanism. So there are many types of torque, but the basic torques which can be devised from these many torques are the deflecting torque, controlling, and damping torque. Any instrument that is deflecting must be controlled and must be damped for getting a good reading. So let's say if this is my reading scale and a needle goes from here to here, so I need this needle to go from here to here, for which I need a deflecting torque. I must give it some torque to move from this point to this point, and after that, after going toward this point, I would need some controlling torque so that this needle stops at a given value, let's say 0.5 volt and 0 volts. I want it to stop here, so this will need a controlling torque, because without controlling torque it will not stop here, it will just go here and touch it. So we will need some spring that will control this thing, and we will need some magnetism that will make this thing go from here to here. And after that, when it reaches here, it will be vibrating because the current makes this needle vibrating. So we would need some fluid inside here so that this motion of to and fro is controlled. So that torque is known as the damping torque. Let's discuss it further. Deflecting torque is responsible for moving a needle to the reading position, and it moves discs like these type of discs continuously for rotational counters. The controlling torque is the torque which is opposite to deflecting torque. So when we say that TD is equal to TC, at that time the needle is giving us a reading. Also the needle is in equilibrium. So when the needle is giving reading, TD is equal to TC. And this is always the case because needle is always static, either at 0 or at some reading. The function of controlling torques are to produce torque equal but opposite to deflection torque, and to bring the needle back to 0 position when the forces are removed from it. Damping torque, on the other hand, works opposite to both deflecting and controlling torque. So if the controlling torque moves a needle from, let's say, here to here, and a deflecting torque moves the same needle from here to here, then if we add some fluid in it, what will that do? That will stop both movement, this movement and this movement as well. So the damping torque is opposite to both deflecting and controlling torque, and it makes the reading visible. This needle will not vibrate, so the reading would be visible. Now let's go into the construction details of the moving system. The moving system should have the following properties. First, moving parts should be light, because we want light instrument and we want less energy for its movement. And the frictional forces should be lesser, because we want the movement to be uninterrupted and we want to get the good reading of the input quantity. So for that we should not include any internal frictional forces. The moving system can be made light by using aluminium so far as possible. So nowadays we use aluminium because it is light. The frictional force can be reduced by the spindles and jewel bearing. So these are used for such activities, and we use many methods for supporting the movement because this is more important. So we want low power and good support for a good instrument. So coming to the suspension type, we are having three types of instrument. First is the suspension type instrument, then there are taut type instrument, and then there are pivot and jewel bearing type instrument. So suspension type instrument are suspended in the air, and its one edge is connected to, let's say, a ceiling, and the other is suspended and having a spring or some mechanism. So the spring has some force which makes this thing to go up, but the weight has some force which makes this thing go down. So the spring force is actually the controlling force, and the down force is actually the deflecting force. And let's say there is a needle which is giving us some readings on the scale. So this needle is then damped using some liquid, let's say liquid in this physical balance. So here one side is suspended, the other is free to move. So this side is free to move, this side is free to move, this side is free to move, and these and these are suspended. This type of instrument is known as compressional suspension, and these are expansional suspension, expansional and compressional, because in this instrument the air column or the fluid column would be compressed. Okay, so such instruments are not suitable for field use, because one must have some vertical suspension for good reading, and clamping arrangement must be having for supporting this system. So if you do not have any clamping mechanism, you cannot use this device. Or even if you support this thing with a vibrating component, let's say you place a hand here and you want to measure something, so this needle would be then vibrating. So we need proper arrangement for such instruments. The taut type instruments are having two sides mounted. This is, let's say, first side, which is having some spring and some spring mechanism. This is the second. So this is free to move, but again we need a vertical mechanism, because if we tilt it like this, then the effect of gravity might change this suspension and might compress this one. So we need a vertical arrangement. So with suspension kept under tension by the spring arrangement, we call it taut suspension. So the suspension is kept in two spring arrangements. Ribbon suspension is also sometimes used. So in a ribbon suspension we are having something like this, and then a vertical column is suspending it. Third one is the pivot and jewel suspension. This suspension can be used in many angles, because due to its mechanism of locking with the jewel. This thing is known as jewel and this thing is known as pivot. So this pivot moves in this jewel, and this is a very small portion, so very less friction is used, and sometimes the spring is used for making this movement a bit more lighter, because if we just press this thing, and it will cause more friction in here, and if we use a spring in it, this will cause this thing to have a bit lesser friction in it. So this is also used in the measurement instruments, and we use either one or two jewels for support of our needles and pivots, etc. Torque versus weight ratio is very much important. This torque is necessary for moving some needle of an instrument. So if this mechanism is heavy, we will need more current and more force to move it. If this mechanism is light, we will need a lesser value of torque required. So if this thing is high and this is low, we will say that this instrument is good. So that's why a high ratio gives us better performance. The movement would be fast, because we'll need less current or less force for its movement. In other words, the needle and the shaft should be light. So when this is light, this will give us good reading, higher reading. Okay, based on the controlling system, we are having two types of systems. One is the gravity control and the other is the spring control. In spring control, we can use it on either angle, vertical, horizontal, and tilted. Such as in these instruments, we are having these spindle and spring control based system. So we can use it in any angle. whereas in the gravity control we use the force of gravity. So this must be vertically aligned. Here the movement is solely dependent on the current that is flowing through this instrument. So this is a linear scale, more current, more movement. But here what we do is that we suspend a thing, and then let's say there is some force in it which causes this thing to move either on this direction or this. Let's say this is the charge and this is a bulb having positive charge. So this is, let's say, negative, and it is moved on this side when we add more positive charge to it. So this depends upon this force, and this force gives us an angle with the gravity. So let's say this is the total gravity, this is the theta with it, so this is g sine of theta. So the force is, the acceleration of the force is on this direction. So if we multiply it with the mass of this and then compare it with this force of attraction, FATT, so we say that the theta is not solely dependent on this force, but F divided by mg and sine inverse, that is our theta. So now this thing is a bit non-linear. So we can say that sometimes we are having non-linear scales if we use the gravity. Not sometimes, all the time, but in springtime, in the spring, we are having all the linear scales. If we compare this spring and gravity control based system, we can see that gravity controls are cheaper, but these are having drawbacks, such as the scale is not linear and we need vertical arrangement for it. We are talking about this effect of current on that spindle. So the deflection was directly proportional to the current, and we introduced a K in it. So the theta is directly proportional to the current that is being introduced inside that mechanism. So this is the equation for that thing, that the K theta, the amount of theta that we get, is proportional to Ki, the amount of current that we give to this instrument. So Tc is equal to Td. Whereas in this second one, the controlling torque is kg sine of theta, so Ki is equal to kg sine of theta, and then the theta is in terms of sine inverse. So sine inverse is a non-linear scale, so there would be a cramped in the end and lighter values in the middle. So it is just like a sine wave. It goes like this. So higher increase, linear increase, low increase. So low, high and low. So the reading would be like this: high, low and high. So the density of the points would be different. So that's why the gravity control is not used that much. Okay, now talking about the damping system, we are having many systems by which we can damp our analog instruments. This type of air friction based damping require a column. So this is an enclosed damping system. This is a not enclosed or open damping system. In enclosed, we are having some piston in which is controlled by the air chamber, and if the piston moves on this side, this vacuum will force it to go back or go a bit smoother. Similarly, in an open system, we are having this, let's say, a fin of metal. When this instrument goes faster, air struck with this plate, and it makes this thing to go a bit in low speed. So both in this side or in this side, this will be reducing the speed of this movement. Fluid is just like this one, and in this we use fluid instead air, so oil or something can be used. Fluid can have a piston type structure or a continuous structure. In piston type structure, we are having this mechanism in which it goes up and down, or back and forth, whereas in continuous vane structure the instrument will continue moving and this fluid will continue stopping it. Eddy current requires a magnetic field. When a metal is passing through a magnetic field, it will be forced to stop by this magnet. So this is actually an eddy braking system in which we use a disc and magnet, and the magnet stops this movement. Now coming toward the PMMCs. PMMCs works on the principle of Fleming lift hand rule, and these are electromagnetic instruments because the current carrying wire is exposed to a permanent magnet, and this permanent magnet makes this coil or this wire to move. So this is typical PMMC in which we are having this pointer attached to this coil, and this coil is pivoted in here and here, and this thing, this hair spring, is actually the control for it, the controlling torque, and this magnetic field in which it is placed. Let's say this is the magnetic field and this is the coil. So this coil moves when the current flows through this coil in this magnetic field. So this is the deflecting torque which is given by this magnetic field and this current. So F is equal to BIL and torque is equal to BIA-N, where N is the number of turns. So we'll use these equations in further discussion. And now let's calculate the deflection torque for this PMMC. Let us suppose that the current that is flowing through this device is I, and its effective length is L, and its breadth is B. So this is B by 2. B by 2 is actually the length on which we can fulcrum this force. So this is a force, magnetic force, and we are fulcruming it on this point. So that's why we are using B by 2 for a single side torque. So torque is equal to force multiplied by B by 2 as given in here, where force is BIL and number of turns. The more the turns, the more the force. So the torque is given by of single side is given by BILN into B by 2. So we are having two side torques in this. Let's say this is a coil. In this side the current goes downward, and in this upward, and this is force here and this is force here. So two forces are acting. So that's why we say that 2 multiplied by T is BILNB. So L into B is actually area. So TD is equal to BI, and L into B is A into number of turns. So this is the equation for TD. Now coming towards the controlling torque. Controlling torque is actually provided from a spring. So spring must have a spring constant Ks, and the more the theta, the more the spring will want this spindle to go back. So this will be more compressed if the theta is more. If theta is 0, so no compression, no force. So when we balance these two forces, K theta is equal to Ki in the equilibrium position, we can get the value of theta as K by Ks into I, which is both are constant, so theta is proportional to current. So this says that this scale is a linear scale. We are using the phosphor bronze springs at this S1 and S2, which are used for this KS. So do check the book for reading a discussion on this thing. Now coming toward the swamping resistance, our circuit is normally balanced by some resistor which compensate heat. So any resistor that compensate heats are known as swamping resistor. So if we have such structure of a galvanometer or PMMC, we will use copper manganese resistor to reduce the effect of current when it goes through this circuit. So if the current goes through this, it is having a very low resistance, so low resistance will heat up this circuit. So for reducing this heat effect, we use a swamping resistor. These are some of the advantages and disadvantages of PMMCs. Let's go through it. These PMMCs are sensitive to small currents, so good for us, very accurate and reliable. It gives 270-degree or more deflection based on the scale that we are providing it. Very effective built-in damping because we are having spring in here, so good damping system. And its power consumption is low because we are having a suspended system which can be moved by just a very little power, and free from hysteresis loss because the permanent magnet is used. Easily adopted for multi-range instrument because we can connect any resistor in it with in series or parallel to get our different instrument ranges. The disadvantages are that these instrument can be operated in direct current only, so AC is not applicable here. The moving system is very delicate and can easily get damaged, so these spring must not be touched or it will get damaged. These are costlier because its making requires much precision, hence these are built with more cost. And aging reduces the magnetism of this magnet. So first point is that the magnetism is reduced with years, and the second is that the tension of these springs would reduce with age. So the controlling mechanism and permanent magnet will destruct with time.